Right. Shh. Okay, simple radio receiver. Right. Okay, so you need to know the block diagram, the function of each block. You need to be able to use that formula to provide capacitor values. So, we have, first of all, the antenna, which picks up the radio signals of all the stations, okay, around, and converts the radio signals. The electromagnetic wave hits the aerial, excites the electrons orbiting, there are free electrons within the metal. Those electrons vibrate and move due to the radio waves. Those vibrations of the electrons are electrical currents, which are then converted to voltages and effectively fed into the tuned circuit, which is a band pass filter, which has a variable capacitor and a fixed inductor. We can then change the value of the variable capacitor to tune the radio to get the correct frequency that you're going to tune into. So that is using the formula F equals 1 over 2 pi square root LC. Remember that? Okay. That then goes to the detector, and what the detector does is it makes the signal have a non-zero average. If you remember what an AM modulated signal looks like, if you took the average of the signal, it would be 0 because it's equally positive and negative. But if we chop the bottom off, we then end up with a non-zero average, which means we can do something with the signal. That could be fed straight into headphones, but first we filter out the radio frequencies using the RF filter, and you are then left with a little weak signal going into the high impedance headphones. They have to be high impedance because we don't want to load the rest of the circuit and draw current from it, because it has no power supply. It's getting its entire energy from the radio waves itself. Okay, so therefore we have no amplifier. It means it has a poor selectivity because the filter is loaded somewhat, and it has a poor sensitivity because anything below 0.7 volts, which if you think is quite a lot, you're just picking it up from the radio waves, anything below 0.7 volts gets chopped off by the diode anyway. So therefore it has to be above 0.7 volts before it even gets through to the filter. So its selectivity, it's able to tune into an individual station, is poor, but its sensitivity, how good it is at tuning into distant or weak stations, is also very poor. It's like a foxhole radio or a crystal radio we did about before. Okay, so the simple radio is very simple. So we've kind of gone through these. Tuned circuit. Generally, AM. This is an AM radio. It picks up between about 300 kilohertz, 3 megahertz is around the range of AM. So one of the advantages of AM is because it's a lower frequency, it travels further because it can diffract around mountains and around the curve of the Earth. Some of it even bounces off the ionosphere and you can hear it even further away. The problem with that though is that you can't fit as many radio stations into the range because you've got a smaller amount of available bandwidth. So therefore the bandwidth of AM radio transmissions is reduced, which means the sound quality is reduced, so it doesn't sound as good as FM. It also means they can pick up more interference because it's amplitude modulated. So anything that's added onto the signal, like noise or distortion, we'll hear at the output of the earphones. Lots of hiss and crackle and so on. So we've gone through this, gone through that. Okay. So, looking at Q factor, if you've got a radio receiver which has good selectivity, it will have some sort of frequency response like that, which fits perfectly over the radio station. This could be radio 1. We've got the carrier in the middle. We've got the upper sideband and the lower sideband. The overall bandwidth is always double the individual bandwidth of the signal that you're trying to send. If we have good selectivity, when we tune in the radio station, it will fit over the transmission like a hat. Okay? And therefore we'll have all of the signal and we'll have the carrier without picking up any of the stations on either side. This one here has poor selectivity in that it's picking up not just this radio station, but half of that one and half of that one. So you hear 2, 3 things at once. That's poor selectivity. So Q factor is the thing that affects the selectivity, and that comes from the quality of the components that you use. Okay, done this, done that. Okay, so here we have a diagram of it all. There's the original amplitude modulated signal. This is the carrier. That is the information signal that you're trying to send. We pick it up. This is when it's gone through the tune circuit. This then goes to the diode, which has removed the bottom half of it. And then that is then smoothed off using the low pass filter, and you're now left with the original signal. So the circuit diagram is as simple as antenna, tuning circuit, diode, low pass filter, and then output. Okay? Sometimes they give you questions on the low pass filter. If you think about the transmission, the break frequency of the low pass filter should be above the frequency of the sound, so above about 5-10 kilohertz, but below the frequency of the carrier. So you've got the audio signal and the carrier, you need to split them, so it needs to be in between the two. So different types of low pass filter need to be set correctly so that they have a reasonable break frequency, using F equals 1 over 2 pi RC. So there's the various stages: amplitude modulated carrier, half wave rectified signal from the detector, and we're left with that. After the RF filter you get that. As I said, the break frequency needs to be just above the audio range of the information signal, usually about 5 kilohertz, and that's the full diagram. Okay, antenna, tune circuit, detector, RF filter, high impedance headphones. The only calculations you need to do: setting of the variable capacitor using the rearrangement of the F equals 1 over 2 pi square root LC equation. They give you that rearrangement on the data sheet, and then calculating suitable values for the RF filter. Okay? So there's the formulas. 1 over 2 pi square root LC to calculate the resonant frequency of the tuning circuit. 1 over 2 pi RC to calculate the break frequency of the low pass filter. That's given on the data sheet. So just a rearrangement of that if you want to find the capacitor value you would need for a particular frequency. Careful of this one, there's lots of squares in it and it's a little bit fiddly. Impedance of a capacitor, 1 over 2 pi FC. Remember, at the break frequency, that is equal to the inductor value, and the impedance of the inductor, 2 pi XL. Okay, I'll leave that there. I'll just do Superhet. Okay, advanced radio receivers, also known as the Superhets. How we improve the radio. You need to know the block diagram, you need to know the function of each block, we need to know about the IF filter and all the subsystems. So, we need to get around the fact that we've got poor selectivity and poor sensitivity in the simple radio. We need to amplify, therefore, the signal that's coming in. To make it more sensitive, we need to basically amplify the radio signal that's coming in to give it a higher voltage. Then it will get past the detector, the diode and so on, and you'll be able to pick up more distant stations. So we can actually boost it using something called an RF amplifier. And at the other end of the thing, we can put an audio amplifier to make it so we can hear it better and have a speaker rather than headphones even. Okay, so we're bringing in amplifiers that we need. Problem is that amplifiers, to amplify high frequency radio signals are expensive and difficult to make, or used to be. So I'm going to skip right to the full Superhet. So what we do is, first of all, we have a tuned RF amplifier. So the amplifier is made so it actually tunes with the tuning circuit to amplify particular frequencies. More efficient that way. We then connect that bigger signal, then gets mixed with a sine wave that's produced by something called the local oscillator. That's this one here. And that means when we turn the link here, the frequency the local oscillator produces moves up and down equally with the frequency that the radio tune is actually tuning into. So we have a fixed difference between the two. This always produces a frequency at a fixed amount above the resonant frequency of the tuned amplifier. So it's usually about 450 to 480 kilohertz above. So there's a difference of that between the two. We then mix the signal together, and that produces an effect known as heterodyning, which is when you mix two signals together of different frequencies, you produce other extra frequencies. 4 of them, in fact, end up in the end. You get the sum of them, of the two frequencies, but you also get the one taken away from the other. So you get the difference between the two as well. So you end up with these 4 frequencies. These are used in things like bat detectors and things like that. If you want to move a high frequency down to a low frequency to do something with it, this can happen this is what heterodyning is. So the mixer does that. It combines the received modulated radio frequency. So this contains the information you want. This is just a sine wave. Mix them together and we get 4 frequencies. Carrier wave frequency, oscillator frequency minus carrier wave, oscillator frequency plus carrier frequency, and also just the oscillator on its own. The one that we want is actually this one, FO minus FC, which is called the intermediate frequency, which is around 450 kilohertz. And because it's the difference between the two, they move up and down like that, that frequency stays constant. Okay? It doesn't matter what radio station you tune it to, what comes out of here is a constant frequency containing your radio signal that you want. That means, what happens is, the intermediate frequency, which we have to calculate sometimes to give you the frequencies you have to do. You have to add them together and work it out. Watch out, it should be around 450 kilohertz for the IF frequency. Carrier frequency, we don't want that. We only want that one. We don't want that because it's even higher frequency, so it's even harder to mess around with. And the oscillator frequency is on its own, pretty useless. It's just a sine wave, so we definitely want that one. And what we're going to do is we're going to actually make an IF filter, which is a very high Q factor filter, which doesn't have to shift frequencies. It can just stay in one position, and because it's built just to filter one frequency, we can give it a very high Q factor. So that means if this has got a high Q factor, the radio must have much better selectivity, yeah? Because Q factor is selectivity. The ability to reject stations on either side and pick up the station you want is the selectivity, and it's the IF filter, and then the IF amplifier, and often we get multiple ones, so it gets better and better and better, focusing on the signal you want. Until then we've got a really powerful, highly selected frequency radio, one particular radio station, then gets put through the detector. So kind of this improves the sensitivity, but all this improves the selectivity. But that then gets fed to the detector. They put it in the same block, that's the diode and the RF filter. Okay, makes a non-average signal, then we can boost it up, make it nice and loud with an audio frequency amplifier, and then make it come out of a loudspeaker like this car stereo or something like that. All radios we have nowadays are super heterodyne. Okay, any radio you listen to in the car, whatever, will be a Superhet, because the others are all awful. You'd know the difference. Okay, So the IF filter is a fixed range bandpass filter with very high selectivity. The reason why it's better is because you don't have to use variable capacitors. The variable capacitors have poor Q factor. Okay, and you can make a better circuit. And that's the rest of the system, as I just said. It's very straightforward. And that's it. Right, I'm going to